Hi, the topic is B trees and B plus trees. This is one of the important topic and is a difficult topic for the students to understand. This is useful in databases. What are the things that are required for understanding B trees and B plus trees thoroughly? This is the list of topics. If you understand all these things and if you know all these things, then you can understand what B trees and B plus trees are. Mostly people try to understand how insertion and deletion is done, just they try to learn the procedure without knowing everything. So this video will be a little lengthy. Reason I am going to cover all these topics that are related to B and B plus trees and help you understand perfectly what B plus tree and B plus trees are. Let me read out the topics. Disk structure, how a disk looks like and how the data is stored on the disk. Then next, when you are storing data from databases, then indexing is used for faster searching. Then what is indexing? What is multi-level indexing? Then we will also discuss what are M-way search trees, and that M-way search trees are converted to B trees and then B plus trees. So this is a little bit lengthy, but I suggest you listen everything, go through it, then you will never forget this topic. Let us start with the disk structure. Let us look at disk structure. Disk structure is like a disk is like a platter on which the concentric circles are made. These are logical circles. This is not physical. And these are circles are called as a track. So let us say this is a track 0, track 1, track 2 and track 3. Then these pieces are called as sectors. So this is sectors and this is also sector like this. Let us say this is sector 0, sector 1, sector 2, sector 3 and 4 and 5. So disk is divided into many tracks and sectors. The intersection portion of track and the sector, this one or this one, all these intersecting positions, these are called as blocks. So any location on the disk can be addressed with track number and sector number. So the address on a disk, that is block address is mentioned in the form of track number and sector number. So like this, if I take this particular block, then this is track 1 and sector 0. This block track 2 sector 1. So each block can have its address in the form of track number and sector number. And typically the block size we take it as 512 bytes. For study purpose we take it as 512 bytes. It can be of any size. It depends on the manufacturer of a disk. So we assume that every block is of 512 bytes. When the disk is read, when we read or write to and from the disk, we always read and write in terms of blocks. Now if I take just one block that is of 512 bytes, the beginning address, that is first byte, is 0 and the last byte is 511, then each byte can have its own address that is called as offset. Let us say this is the 10th byte. So we can refer any one byte on the disk in terms of, first of all, block address, and inside that block we will take offset, that is the address of that particular byte. Every block we assume that the address starts from 0 and last address is 511 because total 512. So any address, any byte, we can take it as address and that address is called as offset. To reach a particular byte on a disk, we should know track number, sector number and the offset. Let us say in this particular block, this particular point I want to read, this is, suppose this is 1 byte. For reading that byte, I should know these 3 things. Then let us understand one more thing. Disk is mounted like this on a spindle and the head post will also be there. So by spinning, it will change the sectors. By this arm movement of a header, that is the header that is reading the data from the disk or writing the data on the disk, by this movement tracks are changed. So we can position a head in a particular track and in particular sector by moving this post, that is head post, or spinning this one. So by spinning, sectors are changed. By moving head, tracks are changed. This is about the disk. Now the data on the disk is always stored in terms of blocks. Now one more thing. Let us take this as main memory. Usually we call it as RAM. RAM is a technology and the type of memory is main memory. We run our programs inside main memory and the programs will access data. Suppose they are accessing the data from the disk, then the data from the disk must be brought into the main memory and then only it can be accessed. And if any results are obtained, then the results are again written back onto the disk. So the data cannot be directly processed upon the disk. It has to be brought into the main memory and then accessed. And this is one important point to understand. And one more term I'll tell you. Organizing the data inside the main memory, that is directly useful by the program. Data inside the main memory that is directly used by the program, that is data structures. And organizing the data on the disk efficiently so that it can be easily utilized, that is DBMS. So study or the methods or the approach used for storing the data in an efficient way there on the disk is all about DBMS, designing, organizing, everything. Now here, study on this one is data structures. Now let us move on to the next thing, how data is stored on the disk. Now let us know how the data is organized on the disk in the form of database. I have an example database table here with some columns and some rows. Let us say there are 100 rows. And how the data is stored on the disk in the form of blocks, already we have studied that. And assume that the block size is 512 bytes. Now this table, the structure of a table is given here. There are more number of fields, I am not showing them there, but here I have written all. So total there are 5 fields and these are their sizes. Employee ID is of size 10 bytes and this is of 50 bytes and the department is 10 bytes, so on. So total it takes 128 bytes. Now it means each row size is 128 bytes. This each row is 128 bytes. Now when we want to store that table on the database, then in each block how many rows can be stored, that is how many records can be stored. So number of records per block. So the block size is 512 and the record size is 128. So this is 4. It means we can store 4 rows of this table in one block. It means that these 4 rows will go into one block and these 4 rows will go into next block. Every 4 rows are stored in one block. So one block can contain just 4 rows. As we have 100 rows here, that is 100 records here, then how many blocks are required? Then for 100 records, how many blocks? There are 100 records and each block can contain just 4 records, so this is 25. So total 25 blocks are required for storing this database table on a disk. Now when this table is taking 25 blocks, imagine if you want to search for any particular record. You have written a query, select from employee table, that is employee table, and I want so and so record for employee ID 5 or employee name Smith. If I am searching, then how much time it will take? So the time depends on number of blocks you are accessing. So for accessing this entire table, we have to access 25 blocks. So number of block access is more, 25. Because the record may be present anywhere. We don't know where the record is present. So we have to search in a table. So for that, at most 25 blocks we have to access. We can access block by block and check for that particular record which we are looking for. But at most 25 blocks we have to access. Can we reduce this time? Yes. Now we will prepare an index for this database table. So index. In index, what we will store? In index, we will store a key, that is employee ID, and pointer to a record. So let us say employee ID 1, this is present here, and employee ID 2, this is present here, employee ID 3, this is present here. So we will have a pointer actually to the table inside the disk, inside the block. So we'll have a pointer to a record. So this we call it as a record pointer. We will have a pointer to a record on the disk in the block. For each record, we will have an entry inside the index. So this is called as a dense index. Next, where do you store index? We will store index also on the disk only. Let us say in this block we are storing an index. This is for index. This is for the database table, and more blocks are there because it is taking 25 blocks. Now index is also kept on the disk. Now the question is how much space this index will take on the disk. Let us analyze. See, employee ID is 10 bytes. Then what about this record pointer, the pointer that we have taken here, the record pointer? Let us assume it is taking 6 bytes. So each entry size is how many bytes? 16 bytes. Each entry is taking 16 bytes. So how many entries are there here? 100 entries are there. Now the question is how many blocks required for this one? So entry size is 16 bytes, right? Now number of entries per block. So block size is 512 and each entry size is 16. So this will be 32. So it means we can have 32 entries in one particular block. So total how many entries are there here? 100 entries. So for 100 entries, 100 by 32. So how much this is? 3 point something. Let us say 3.2. Just assume it is more than 3. So it means that we require 3 plus blocks for storing this index. So let us say 4 blocks are required for storing this index. Now whenever we want to search, we access index. So at most how many blocks we require? 4 blocks of index. And once we got a particular key, let us say suppose I am looking for this, using that address I can access the record. So for accessing the record I have to access one block. So maximum 4 blocks of index and 1 block of database table. So first search in the index, at most how much time? 4 blocks. Then once you got the index entry, then go to that particular block of database. So that is one more block. So total 4 plus 1 blocks are required for accessing any database record. For accessing any record, we have to access 4 plus 1. That is just 5 blocks, not 25 blocks, because we don't have to look into the entire table. This is the benefit of index. Now next I will talk about multi-level index. Next, what if the index size is also growing? How? Instead of 100, now I have 1000 records. 1000 records means 250 blocks. Now here we require 4 blocks. Now we require 40 blocks because there will be 1000 entries. Just I am adding 0 to it. When the rows were 100, we require 4 blocks. Now 1000, let us say 40 blocks are required. Just assume, I am not doing all calculations. Then the searching in the index itself is larger. So can we have an index above an index? Yes. Now how you will prepare this index? For every entry here, shall we have an entry in this next level index, high level index? No. For each block. So how many entries can be possible in this block? 32 entries. So we will have one pointer to 32 entries of this particular index, right? So let us say the starting key is 1, right? Next key will be 33 and it will be pointing on to the next block. So this is a sparse index. It will not have each entry for one entry here, like it will not have the same number of entries. It will have one entry for one block of index. Now, as I said, there are 40. Now, again, what is the size of this one? Just 16 only. So, how many are possible? 32 are possible in one block. Then, for this particular index, how many blocks are required? Just 1 plus point something, let us say 2. So, 2 blocks are required. So, this high level index can be stored just in 2 blocks. So, database table in 250 blocks, first level index 40 blocks, then next high level index just 2 blocks. So search in 2 blocks. Once you get an entry, access a block here. Then once you get an entry, access a block here. So total how many blocks? 2 blocks from this side, 1 block from here, 1 block from here. So in this way, by adding one more level of index, we are reducing the number of block access. So this is the basic idea originating for B and B plus trees. I will just draw multi-level index and then I'll show you how it looks like. Let us look at multi-level index once again. Suppose this is the main index. Now above this we need one more index. Suppose this is too large. Then how this will be having? It will be having a pointer to set of entries in an index. Then a pointer to set of entries in an index. I'm just taking randomly. I'm not drawing every counting and drawing. So this is having a pointers to these. Suppose this is also large. This is also large. Then you can have one more index which will have a pointer to set of entries and a pointer to set of entries. This is how we can go on adding multi-level index if the database table, suppose here is a database table, and if size is growing, this index will grow and we will add one more index, one more index. Adding multi-level indexes will reduce the number of block access. So if I just turn it around and see it like this, next level index, then next level index, if I turn it around and see this is how the multi-level index looks like. Now what is the requirement of multi-level index? Shall we add the index by manually? Shall we check that the database size is growing and then we should add indices one by one, that is high level indices? No, we want the high level indices to be added automatically and deleted also automatically. If this is increasing, table size is increasing and this index is increasing, then you add one more index. If you are deleting the records, then the indices size will reduce and then you remove the high level index. We want self-managed high level indices, that is multi-level indexing. So the final thing is we want self-managed multi-level indexing, and that's how it gives the idea of B trees and B plus trees. So now you can see that this multi-level indices are looking like a tree. If I just turn their side up, then it looks like this. B trees and B plus trees are actually originating from M-way search trees. So next I will discuss what are M-way search trees. Then finally we'll go to B trees and B plus trees. Let us talk about M-way search tree. See, for knowing about M-way search tree, let us recall about binary search tree, which is useful for searching purpose, and for searching any key value, we start from the root, and if the key value is smaller, we go on the left hand side. If the key value is larger, we go on the right hand side. Like this is a binary search tree. If I am searching for 15, then 15 is greater than this, I'll go this side. 15 is smaller than this, so I'll go this side and it is found. So we know that the smaller keys are arranged on the left side and the larger keys are arranged on the right side. This is what done in binary search tree. In binary search tree, how many keys we can have per node? Just one key. And how many children each node can have? How many children? There can be 2 children. Each node can have maximum 2 children. So that's why it is called as binary tree. Binary, bi means 2 children. So it means, can we have a tree with more than 2 children or more than 1 keys? Let us check. 20 and 50. These are the 2 keys. Now this side I will have the keys which are smaller than 20. So that is 10 and 15. And here I will have the keys that are in between these two. That is 30, 35 and here I will have the keys that are greater than this, so that is 60 and 90. So yes, we can have a search tree like this also. This is a search tree. This is the following the idea of same as binary search tree. See, the keys are arranged such that they are in the increasing order. So if you see the keys here, see, first key is smaller than second key and smaller than third key. If you have more keys, they will be arranged like this. And if I am searching for 30, then I'll start from here. 30 is greater than 20. 30 is less than 50. So it must be in this child. Come here, 30 is found. So no doubt the amount of time taken for searching is little more than binary search tree, but the approach of searching is same. So these trees are called as M-way search tree. So what is this M-way? See how many keys it is having. In this example, it is having 2 keys. Then how many children it is having? So each node can have maximum 3 children. So this is 3-way search tree. This is a 3-way search tree. This is called as 3-way search tree. So in this way, M-way search tree means what? A search tree in which each node can have at most M children. M-way search tree. So each node can have at most M children. So how many keys? M minus 1 keys. So M is based on the number of children, that is the degree of a node. So M-way search trees are the extension of binary search trees, you can say, or else you can say binary search tree is a type of M-way search tree with a degree 2. So you can have degree 3 also, degree 5 also, degree 100 also, degree 1000 also. So it means you can have 100 keys here, and each node can have 100 keys and 100 plus 1 children. So you can have any degree of search tree. This is about M-way search tree. Let us look at the node of M-way search tree. Like for binary search tree, how we prepare a node is, we will have data here and 2 children. Then here you need more number of children. So let me draw the node for this one. If the M-way search tree is, search tree ST I am writing, is suppose 4-way search tree, means each node can have 4 children and 3 keys. Let me draw a node structure. This should be a child pointer to the child, and this is key 1, and again this is a pointer to a child, and this is a key 2, and this is a pointer to a child, and this is key 3, and this is a pointer to a child. So 4 child pointers, so this is 4-way, and when it is a 4-way, then there can be 3 keys. That is M-way search tree, a node can have M minus 1 keys. So it is just like this. This is a diagrammatic representation, and if you are making a data structure, then the node structure looks like this. So if there are M children, then M minus 1 key spaces are required. Now next, can we use this search trees, these nodes structure for preparing index? Let us see. So I will try to use this for making index. So let us check how we can do this. For 4-way search tree where there can be 4 children, so this is a child pointer. Okay. Now this is key 1, and this is the next child pointer. Then this is key 2. Then this is the next child pointer. Then this is key 3 and 4th child pointer. So child pointer 1, 2, 3, 4. Then what is this I am adding? See this. After every key I have a pointer. This is nothing but, see, if you have keys here and you are taking a M-way search tree, benefit of M-way search tree as an index, then apart from the child pointer, you should have also a pointer to a record. That is a record pointer. So yes, we will also have a record pointer. So this is a record pointer. A record pointer. So we can utilize M-way search trees for indices, that is multi-level indices. Like tree will have multiple levels. So for making multi-level indices, we can utilize M-way search tree, but the node structure should be like this. So just remember this node structure. See, keys are there and child pointer. So 4 degree 4, so 4 child pointer, 3 keys, so 3 record pointers. For each record, for each key, there is a pointer to the record, to the database record. Now, if we simply use MV search tree, what will be the problem and how we can overcome the problem, and we introduce B trees. Now we are going towards B trees now. Till here we have discussed about MV search tree. Now I am taking you to B tree, and in B tree we will use the same node structure. Just remember this, again I may not be showing you. This will be the node structure that is followed in B trees. But first of all, let us know what is the problem with MV search tree, then how B trees are different from MV search trees. Let us see how insertion is done in MV search tree and what is its problem. Then we'll move on to B trees. For that, to make you realize the problem, I have taken 10-way search tree. 10-way means degree 10. Means each node can have 10 children and 9 keys. And suppose I have to insert these keys. Let us see how I can insert. First 10, there is nothing, so I will create a node and insert 10. How many more keys I can have here? 8 more keys I can have here. But for inserting 20, I will create a new node as a child and insert 20. Then inserting 30, 10 that is smaller, 30 comes on right side, so I will not insert here, but I will come to this, and 30 is greater than this, so I will insert 30 here. So I can insert like this also, but this is wrong. I should first fill up this node, then only I should think of creating next node. But there is no control on MV search tree. You can insert as you like. So it means if I have n keys, then what will be the height of MV search tree? N. So this will be too much time consuming. It becomes similar to linear search. That's the problem with MV search tree. So what is the problem with MV search tree? The creation process is not under any control. There are no guidelines for creation process. You can create as you like. If suppose you are creating it like this, then it's a waste of time. It will take a lot of time for searching. Then there must be some rules or guidelines for creating MV search tree. Yes, those guidelines are called as B trees. So B trees are nothing but MV search trees with some rules. Let us see what are those rules. I'll explain them. Let us see what are B trees. B trees are nothing but MV search trees with some rules. So what are the rules? Let us see. See, the first thing. Every node you must fill at least half. Half what? If the degree is m by 2 children must be there. So m by 2 seal value is taken, not floor, m by 2. Means if degree is at 10, means 5 children must be there for a node. Every node must have 5 children. Then only you think of creating new node. That's what, to control the height of MV search tree. This is the rule. You can create a next node only if the current node is at least half filled with children. This is one. N by 2 children must be there. Then second thing, how we can impose this condition on a root? We cannot impose this condition on a root. If we impose, then we cannot insert even a first value also. So root can have minimum 2 children. So root means the first one. So first node can have minimum 2 children, right? So it means it can have just one key also, no problem. But what about all other nodes? They must have at least half of the children. This is the conditions, 2 conditions. Now third conditions. Then the third rule is all leaf nodes must be at same level. All leaf at same level. That's it. These are the 3 things if we are following for creation of a MV search tree. So actually we are creating B tree. And one more important thing here is that the creation process is, fourth point is, the creation process is bottom up. Creation process is bottom up. So now I will take some keys and I'll show you how a B tree is generated from bottom up. So for that I will not take a 10-way search tree. I will take a small degree tree and show you how a B tree is created. In other words, how insertion is done. We will create a B tree of degree 4, means each node can have 4 children and 3 keys. So I have taken some of the keys here, then I will be inserting more and more nodes. So I will add more keys afterwards. Let us start. First, there is no node at all. First key I am inserting. So that is 10. First key. So it can have how many children? 2 children. And as per the multi-level index, when we said, then it can have one record pointer. The next 20. 20 will be inserted here. That is greater than 10. 40 is inserted here. Next is 50. There is no space for 50. Already 3 keys are there. Degree is 4. So we cannot insert 50. 50, there is no space. Then what we should do? Split this node and create one more node. So out of 10, 20, 40 and 50, 2 keys I will keep this side and 1 key I will send this side. 40 I will send it in the root. Then this is the left child, this is the right child. That's it. So when the node was filled, there was no free space. Then for inserting a key, we have splitted a node and one of the key we have sent it on the root. Out of 4, including 50, out of 4, 2 this side, 1 that side, 40 up. This is how splitting is done while creating a B tree, and you can see that the tree is growing upwards. So that's it, it's created bottom up. And I was telling you that B trees are useful for implementing multi-level indexing. Then if you say this is one first level index, then above that this is the second level index created automatically. If you add keys here, automatically this is created. Now let us see, I will add more keys here, then again you can see that this is growing. So let us continue. I will insert few more keys. Let us say 60. So 60 comes here, then 70. 70 comes here, then 80. 80, there is no space here. 80 should come here, there is no space. Then split again. Then what I should do? Including 80, 50, 60, 70 and 80. So 80 should go this side and 70 should be in the root. This is the child. Now the tree looks like this. Then next I will insert 30. 30 will come here. Then I will insert 35. There is no space for 35 here. Then split. So as there is no space, I will split this side. So out of 10, 20, 30 and 35, this should go in the root, and 10, 20 this side and 35 on this side, right side, 35 on this side. Then who will go in the root? 30. So I will redraw it. 30, 40 and 70. I'll remove this. Yeah, watch here. This is the child, this is the next child, this is the child, and this is the child. This is how the tree looks like now. See, whenever the node is becoming filled, we are splitting it and we are sending one of the key in the parent. Now we'll try to fill few more keys here and let us see. I want to insert 5. So where 5 will come? 5 will come in the beginning. So 5, 10 and 20. Now I want to insert 15. 15, there is no space. So 5, 10, 15 and 20. There is no space for 15. Then arrange them in this order. Then there is no space, means split it. So for splitting, I will create one more node on this side. 5 and 10 this side and 20 this side. Now 15 should go up here. This should go up. Right? Achha, one more point. You will be thinking that why I am sending third key. I want to send second key. Okay, that is your choice. So you can make it either left biased or right biased. So either way you can do that. Now it is left biased, means it is more keys are on the left side. So whichever one you want, you can take it. So 15 moves of 20 on this side and 5 and 10 this side. Now there is no space here also. So here also you split it. So out of how many keys? 15, 30, 40 and 70. So 15 and 30 this side, 70 that side and 40 in the parent. So this will be on this side, this will be on this side. Now all these links will also change because we are splitting it. So this is on this side, this is on this side, this one, and I will draw it little far from this one, 70, then 70 is left and 70 is right. So now you can see there are three levels, 1, 2, 3. So three levels of indices are created, and this is how B tree is generated by inserting keys. And the height of a B tree is increasing, and this is same as multi-level index. So this is the creation process. So it's under control, and all leaf nodes are at same level. So they are looking like more like a index, and this at same level. This is forming an index, and above one is also an index. So I have shown you how to insert and how to create a B tree. Now let us see how it is useful for the databases. Just minor things, very important and key points I am showing you. As we discussed just now that every node will have a pointer to the child node as well as record pointer. This 20 will have a record pointer, 5 will have a record pointer, 10 will have a pointer, 15 will have a record pointer, 30 will have a record pointer. Every key will have a record pointer also that is pointing on the database. So this is useful for implementing multi-level index. Apart from the child pointer, this is a record pointer. So a B tree node can have what? Key, child pointer, that is a block pointer, and this is a record pointer. That's it. That's it about B trees. I did not show deletion. It depends how much you have understood from this one. Just you reply me back, leave your comment, and if required, I'll prepare deletion also. Okay. Actually, I wanted to show you what is the application of B trees and B plus trees. So I have started my topic right from indexing and brought you up to this point so that you can understand the relation with the databases and B trees. Otherwise, mostly people study just about B trees and B plus trees without knowing indexing and databases. So now you can relate it with the databases. Now the last thing, what is B plus tree? It's a very simple thing. Let me show you quickly. Just I will modify this. What is B plus tree? In B plus tree, we will not have a record pointer from every node. We will not have a record pointer from every node. We will have record pointers only from leaf nodes. Only from leaf nodes will have a record pointers. Then what about these keys? Every key will have its copy in the leaf node. So means who is missing here? 15 is missing here. So 15 will be here also, 20. So 15 will have its copy here also. So there will be record pointer for 15 also, 20 also. Then 30, here will have a copy of 30 also, and 35. So what about 40? 40 we will have a copy here also. 40 will be having a copy here. So 40 and 50 and 60. So 3 record pointers. So 70 will also be present in this one. So every key in the tree will definitely present in a leaf, and these leaf nodes are connected like this, like a linked list. So this becomes a dense index now. This is exactly like multi-level indexing. So this is B plus tree. So what are the differences from B tree to B plus tree? Let me quickly tell you that all the keys are present in the leaf nodes, and in non-leaf nodes their duplicates may be present. Every key must be present in leaf, and there are no record pointer from non-leaf nodes. The record pointer will be from only leaf nodes. So leaf nodes, all leaf nodes, as they are at same level, they will form a linked list. These are the points. Then this becomes a dense index. This becomes a dense index. Then this is a sparse index, next level. The next level is sparse index. So rather than B tree, B plus tree is more like multi-level index. So what is plus in this one? That I have shown you. So if you understand B tree, understanding B plus tree is not difficult. That's all with this topic. There is an analysis and a lot of things are there. So it's a big topic. The purpose of coverage of this topic was to relate it with the databases. Alright, so I have covered more from the database side than just B trees and B plus trees. So just B trees and B plus trees can also be taken as a topic and discuss. Leave your comments, let me know. If required, I will prepare a separate video.